We are again going to use the limit comparison test that we've been working with to show that a series, whether or not a series converges or diverges. And we're going to be dealing with this first case here, where if we have some sequence A and some sequence B, and they're both greater than 0, then if the limit as n approaches infinity of our A sub n over our B sub n sequence equals some constant which is greater than 0, now that could be 1, it could be anything, then both as a series either converge or they both diverge. One or the other will be true. So let's just see our example here. So here we have the series from n equals 1 to infinity of all of this, which is the root of n squared plus 10 minus n. Now, this looks a little bit curious here because we have n going to infinity, and you could argue that, oh well, as n goes closer and closer to infinity, this plus 10 here is not going to matter, and then root n squared is just going to go to n, and then n minus n, well, that just goes to 0, and you could see how maybe possibly it could converge because the limit of the expression does go to 0. But in order to evaluate this properly, we have to do a little bit of algebra and then take a look at our limit comparison test to see if that does indeed make sense. So to sort of algebraically manipulate this to get it to a point that we can use here, I'm just going to multiply this expression by its conjugate. So we're going to multiply this by n, the root of n squared plus 10. Now instead of a minus, we're going to have a plus n. And if we're multiplying that by that, we can divide by this. And this is just going to be the same as if we multiplied by 1. So if we multiply it by something divided by that something, that's just the same as multiplying it by 1. But now we can just sort of tease out an expression that's easier for us to work with. So via the difference of squares, let's just take a look at algebraically what the difference of squares looks like. If we have, just as a side note here, if we have a minus b times a plus b, this equals a squared minus b squared. And if you don't believe me, or if you need to just stop and take a moment to prove that to yourself, go ahead and pause the video and do so. I encourage you not to just take my word for things, but you'll always learn more if you just go through all of the steps on your own. So by this logic here, we can just pattern match here, and we could say that our a term here is going to be this root n squared plus 10. So we're going to have all of that squared, which is just going to give us n squared plus 10. So we could say that this is equal to the series n equals 1 to infinity of n squared plus 10. And I'm just going to put that in brackets like that, just so we don't get it confused with our b term. Our b term is just going to be this n here, so that's going to give us a minus n squared, according to our difference of squares. And then we are just going to have all of that over root n squared plus 10 plus n. So root n squared plus 10 plus 10. So now we have some addition, which hopefully would make this a little easier to work with. Notice that we have n squared here, and over here we have a minus n squared. So our n squared terms in the numerator are just going to cancel each other out. That's just going to give us a 10 on top. So this is the series from 1 to infinity of 10 over all of this. And notice that as n goes closer and closer to infinity, well, this just equals root n squared, or this is just going to go closer and closer to root n squared plus n, or n plus n, because the 10 is going to become increasingly insignificant. So you could argue that this series is going to be smaller than this series. It's going to be smaller than the series from n equals 1 to infinity of 10, which is what we had over here, over simply 2n. And this simplifies. 10 divided by 2 is 5. We could pull the 5 out of our sigma notation. So in other words, this is greater than this, which is equal to 5 times the series of n equals 1 to infinity of 1 over n. Well, what do we know about this series? Well, this is just the divergent harmonic series. So we know that some greater function here, and obviously because it's divergent, it doesn't matter if we're multiplying it by 5. That's just like saying 5 multiplied by infinity. It's still infinity. Because this is our greater function and it's divergent, we still don't know whether or not this is convergent or divergent. So in order to figure that out, we're going to have to take this expression here and use our limit comparison test. This expression that we sort of algebraically teased out from the series that we started with. So let's just go back to our definition here of the limit comparison test. Let's let 5 times the series of the harmonic series. This is going to equal our b sub n. So in other words, this is our known series. We know the outcome of this. It's divergent. This is our known series. And likewise, let's let the series from n equals 1 to infinity of this, the one that we want to know. We also said that it equaled this, so I'll just go ahead and write that as well. It equals 10 over n squared plus 10 plus n. Let's say that this equals a sub n. This is the series that we're testing. So we have our known series that we're going to put on the bottom of our ratio, and then we have the series that we're testing that we're going to put on top. So then, using our limit comparison test, we can write the limit as n approaches infinity of a sub n over b sub n is the limit of 10 over root n squared plus 10 plus n over 5n, 5 over n, sorry. And this is just going to go to, I like to use the little arrow to show what it eventually goes to. So obviously the 10 divided by 5, this is just equal to 2. And the n down here, we could just flip that and put this up in the numerator. This in brackets here is just going to get pushed down to the denominator, if you want to think about it that way. So this gets flipped up to the top, this gets pushed down to the bottom if you work out the algebra. This is an equivalent expression here. sorry, that's plus n. Yep. Plus n. Okay. Well, this just goes to, as n approaches infinity, this just goes to 2n over n plus n, or 2n. So this just goes to 2n over 2n, which just equals 1. And we have an outcome of 1, which is greater than 0. It's some constant greater than 0. And we also know that B sub n diverges. So therefore, just by our limit comparison test, A sub n also diverges as a series. So we go back to our original series here, and we have that this whole thing right here, this one that we started with, this diverges. It diverges via the limit comparison test.